Yeah, I'm setting up for a shoot now. I better turn some lights on. And my back wall isn't really blue. I turn these... Here, that's not blue. I turn these blue lights on, and look at this. Look at that. I turned the blue light on. See that? And that is Compton effect. I did something bad this morning. I called somebody a dummy. I was watching YouTube and I made a comment. My first words in this comment were, "You dummy." And that's bad because this person wasn't a liar. They were simply barking up the wrong tree. I just get so tired of it. I get tired of the something for nothing people on YouTube. You know, they're enamored with resonance. And it is true that with a very small amount of power, if you have a resonant circuit, you can make a tremendous amount of current. But you're not doing anything about the power. It has to do with Q. And Q is X sub L or X sub C over R. And so, as resistance gets lower, current's going to get very high. And you know, a coil of wire shouldn't have too much resistance. Maybe it's a small coil. And a capacitor, you can make the leads fat, and it has very low resistance. So you get a tremendous amount of current, and people get confused over this. And look, they're in good company. I shouldn't insult them, because after all, before Steinmetz, the Royal Academy had it wrong. Poor Ohm. First they said Ohm's law doesn't work because their batteries were junk. And then and they performed the experiment wrong. And then they said Ohm's law doesn't work for AC. Yes, of course it works for AC. But until Steinmetz, they didn't realize the current is sometimes out of phase with the voltage, because this is not the same as resistance. It looks the same sometimes. So Steinmetz gave us true power and apparent power. And that's what these people are dealing with. They are so amazed at the phenomenon of resonance that they think they're getting something for nothing. So today, instead of talking about something for nothing, I am going to show you where I think we can get the energy for free. That is, hey, you want free energy? Try available energy. And I'm going to show you where the available energy is that we can look at for the future. Now, you know, I'm the person who broke the second law of thermodynamics. Now, the way I did it, it was so easy. I'll put a little clip in there. No one has built this thing yet. Why? No one really questions any part of it. It's clear that heat rises. It's obvious that the thing probably works. And so people look at it and they say, oh yeah, I guess it works. But then some people say, but that doesn't really do anything. Well, actually it does do something. It does something that is most important in astronomy. Because you notice the universe is not just plain dust. It's not totally disordered. It's got all kinds of structure out there. And so, well, you know, some astronomers say eventually all that structure will disappear because of entropy. Everything is going to be all mixed up and it'll just be a cloud of, you know, dust. Well, we have forces, and forces counter entropy. And this is the real point of my experiment. For example, gravity. Gravity counters entropy. Now, we notice the universe is, it does have order. And, you know, I'm a steady state person. I have a steady state video on here. I'm not a Big Bang person. And the Big Bang is falling like crazy. Now my steady state video is the norm. Because the Webb telescope. So the universe is quite old. I think it had no beginning. I have no problem with the concept of infinity. I don't feel any need for constraints on endpoints for time. There are those on YouTube that say time doesn't exist, time is an illusion. That's called clickbait entertainment. So let's go to where the available energy is. And I'm going to give you 2 of them. I'll give you 3. Now, the first one, I have to plug my own experiment. And it's very easy. And it uses a thermoelectric generator of the available type. You can call it TEGs. You can look them up on eBay and order a dozen for $15 or something like that. I did. So, and they've served me well. I bought them for a project I was going to do. I was going to put them on the outside of a catalytic converter and then put a heat sink outside that, and you don't need a generator for your car. Of course, that's an internal combustion car, and I'm working on my electric car, so I don't care about it anymore. And they sat on my table for the longest time. I have to do this experiment to try to break the second law. And I tried to look up on the internet what was the very most sensitive TEG. Well, all it had was the same ones that were sitting on my counter. So I used one. And I was shocked at how sensitive it was and how well it worked. And you'll see that on my video. So there is one way to do it. But you know, I get this minuscule amount of power. Because a chamber of air, which is what I was using for my Maxwell's Demon experiment, doesn't have that much energy in it in the first damn place. And then you're not looking at all the energy. You're only looking at the difference between the fastest and the slowest molecules. And you know, you're going to have a Boltzmann distribution of temperature. And here's the number of right here. This is number of atoms, and this is temperature. And you know, most of the atoms are going to be somewhere in the middle. Look at the bulk of them are right here. There's not enough temperature difference to do anything about. And so the only temperature I can get available energy out of is these high energy and low energy tails. And what happens is simply that this tank of air, which is all at the same temperature, a box of air, that's what I used for my experiment. The very warmest ones rise to the top. The very coolest ones fall to the bottom. And you'll notice this, if you have a room that's all at the same temperature, close the door and leave. And come back in a few days and get on the step ladder. Reach up there like you're changing a light bulb. Hey, it's warmer at the top. Now this is very clear in the winter, but you know, people don't, well, it's clear all year long. But people normally assume it's because, well, the hot air that the heater blew in, or the sun, or something else, the sun goes through and warms up the ceiling. It's all true. But it's not relevant to this, because if you isolate this in styrofoam, which I did, it still happens. It happens spontaneously. However, that isn't... that was capturing microwatts, and hard to power your house off of it. You want more power from that? There's a way to do it. The ocean. And this has been tried before. Ocean thermal, and you can look it up. It's called OTEC. And it's so difficult, it didn't work. That is, it didn't work. They couldn't make it feasible economically, and I can understand why. They were trying to pump up the cold water from the bottom of the ocean and use the temperature difference with the surface water. In principle, it's fine. In practice, it's very difficult. So, I have a better way. Now, all you need to do, and this is a job for genetic engineering, all you need to do is engineer some, maybe they're just little seeds, who knows, it's a plant. And this plant will grow up, you drop it in the ocean, and it grows into big old telephone poles of graphene. And hey, the carbon is available in the ocean, and so why not? So this thing has a great big graphene trunk, and it goes from the bottom of the ocean where it has, a graphene conducts heat like a couple thousand times better than copper. So it's wonderful stuff, but I don't have any. And so these big tree trunks of graphene will grow up toward the top, and then all we have to do is slice the top off and put our thermal, and that'll kill it. Then you put your thermal electric generators in the middle and put the top back down. But that's what it would take. It would take thousands and thousands of these graphene telephone poles in the ocean to, so it's a challenge. I do suggest doing it that way. But now, another thing about these graphene plants that you're going to grow for us, the plastic that we put in the ocean, all the microplastic and stuff, it clings to the outside and makes like an insulating foam. So, you have your work cut out for you, you genetic engineers. Do something other than trying to screw up our wheat, okay? Now, people think the ocean is cold at the bottom because the sun hits the top, but it never gets to the bottom. That is not why the ocean is cold at the bottom. Because if you wrapped a blanket around the earth, it would boil. If this blanket, it would reflect all the sun. No sun can get to the earth, but the earth cannot radiate any temperature out, any heat out, because this blanket is insulated. It's like a 50-foot layer of styrofoam. And I don't know how it got there. It must be one of those terrible genetic engineering experiments you did that went wrong. But if you did that, and the Earth was perfectly well insulated, well, it's got a nuclear reactor in the core. And you notice if you dig down, it gets warmer. So the sun hitting the surface of the ocean is nice, but it's incidental. Now, let's get back to that hole you dug where it was so warm down there. Geothermal. It works. It's nuclear. It's nuclear at a safe distance. But, I get tired of digging. I have a shovel. It's not so easy. Geothermal is not so easy. But it's an available source. But I'm going to give you an easier available source. And it's the same thing. It's the warm earth. Those same TEGs that are sitting on your counter from ordering them from eBay. You lay them on the ground at night with a heat sink on top. And all the heat comes up. Now, this doesn't work everywhere. But in the desert, it surely works. I'm in Las Vegas. In the summer, the heat definitely to the ground during the day and back out at night. And if you could harness some of that, that is energy. I was going to actually film this experiment in my backyard, but now it's winter. So if I can get around to it before I forget and it's hot outside, I will try putting a heat sink on top of a TEG, and I'll put a voltmeter on it. We know it's going to work. We just don't know how much current. They do very well. Those things do very well, especially if you can get one side 20 degrees centigrade colder than the other side. Then they really put out. And of course, if you're starting at very low temperatures, that's bad. So high temperatures work better than low ones. I'm not suggesting that as a world-saving technology. It definitely does work. But I'm going to tell you where there's more available power. This is something that comes to us from photonics. And boy, is it difficult. But it's not impossible. I want to mention it this time. I have no college degree. So you don't have to worry about me being one of those bad people who's suppressing knowledge because of my college degree. But I did take some classes. And I learned about Compton effect. And Compton effect is when you shine, well, this guy Compton, he took an X-ray machine and shined the X-ray at the atom, and the atom radiated 2 photons out. Instead of just re-radiating the X-ray, it re-radiated 2 photons. It split that X-ray photon into 2 lower energy photons, like maybe a UV and a visible or something like that. Because, you know, you keep the electron up a couple levels, it comes down stepwise. Now, I discussed with my chemistry professors, you know, the world used to be different. Before terrorism was a big thing and all that stuff, you used to be able to hang out places like chemistry departments. Well, my chemistry teacher's office hour was in an office full of chemists. And so I'd come there and I'd use up their unused office hour time. And I would have a whole gaggle of chemists who would join in the discussion. So it was great. And many of them became friends, and I took a lot of courses for free. I audited courses. And, you know, here's something you can get for free. You might not be able to get a lot of free energy, but you can sure get free education. And I'll tell you how. Now maybe this isn't possible anymore. I took extension course. I took 1 extension course at UCLA, chemistry. And you sit in the same classes with all the other people who are taking that course. They're admitted students, but I was not. So then I got to know some of those professors. And even some of the ones I didn't know, I would ask, do you mind if I sit in your course? I never got a no. I never got a no. Now, sometimes I had to wait a couple of weeks until there was room to sit down, otherwise I was standing. Don't worry, plenty of people drop that course. So you can get a free education. Well, maybe not free, but you can do better than I did. You can ask the professor, hey, do you have any lab assistant positions open? And you can become a lab assistant and get a little money while you're taking all your courses for free. Now, I was not able to take the tests on the courses I audited. Oh, too bad. That's not an obstacle. You don't care if you take the test. You care if you learn something. So, free energy? No. Free education? Yes. And then there's YouTube. I've been taking those MIT courses, like the one on atomic solids. See, because I didn't take that much chemistry. I didn't go for about 1.5 years. So, I liked those courses. A lot of it was review, but some of it was not review. And I never did XRT. So it was very good for me to look at that stuff on YouTube. Not that I have the machine for it at home. But back to energy. So, when I learned about Compton effect, I discussed with all these chemistry professors, was it reversible? Did it happen in nature? I had nothing to go on. I had no experimental data to point to at all. I just surmised that at some point it was a possibility that 2 photons had struck an atom and that it had resulted in an electron getting kicked upstairs and then coming down coming down through a couple of levels and emitting a higher energy photon. Now, total conjecture on my part, and everybody said, So, they did it. They did it in photonics, and it was so difficult. What they did, they supercooled, I think it is cesium atoms. They're always using cesium atoms. So they supercooled it and found that when they did that, and I don't know, it was very cold. colder than I can get it, they could have a window of time that was big enough that you could shoot a photon at the thing, have it bring an electron up a level, and then shoot another photon at it and bring it up another level, and then watch it decay down to level 0 and put out a higher energy photon. And it is called parametric, I don't know, but it is the constructive interaction of two photons. I want to capture the energy from ambient temperature in solids. For example, I want to power a solar cell. And to power this solar cell, I want to use the radiation that's happening all over the place, say from the walls. Now, that is not possible because that radiation is at a very low frequency. So here's the deal. We need to increase that frequency by a factor of about 20. We can make that microwave stuff, radiation, inside everything, ambient temperature, we can make that push a solar cell. So, did I say it was easy? No, you did not hear me say it was easy. I have never witnessed this phenomenon, and it looks like I never will, because they had a cryogenics lab. I won't be attempting that one. All it proves is that Compton effect is reversible. It is reversible and has been reversed. So, keep going with it. It could be a long time, and probably forever, before that one will be done. But I am doing this video today to tell you the real sources of free energy. And they don't come from nowhere. The energy has to be there already. Now, I am a believer in the law of conservation of energy. Not everyone is. Sabine Hossenfelder, the famed YouTube physicist, she says she doesn't believe in it because of, I'll try to put it the way she put it. She said space growing as a source for redshift, which she assumed, the Hubble constant, was proof that the law of conservation of energy did not hold. And what I say to that, which I said in a previous video, is that's the best argument I ever heard against space growing. So if space isn't growing, then what? Why is everything moving away? Well, we don't know. Now, can we say that? Can we say we don't know? Is that okay? It could be in the future we'll have a better picture. As we look at the web, not the internet, the Webb telescope. We need a Webb telescope that'll look at the internet. And that way we can keep the internet very far away from us. But anyway, if we look at the Webb telescope pictures, we see galaxies outside the boundaries of where the Big Bang should have taken us, outside of the universe. So they're obviously wrong about that one. We realize that. We don't know what's out there. And one thing that could be out there in every direction is mass. We can't see it, but it doesn't mean it's not there. We could be in, I did a steady state video in which I likened our known universe, our observable universe, to a puff of smoke. And it's a good analogy. You should look at it. It's steady state versus Big Bang. In this puff of smoke, which is, I say smoke because I was calling the universe a colloid, where we can see through it in some places, but it gets cloudy. That's a colloid. There you have it. There are a couple of sources of available free energy. And of course, I'm using the most available, and that is solar. And the second most available is wind, but I certainly haven't been able to harness any near my house that was worth a damn. The solar cells really beat the wind by a factor of 50 at my house. And I will also say those eBay windmills, no good. Don't buy them. Stick to the solar cells. You know, I apologize to the poor YouTuber who I called a dummy. But you know, I get tired of it. These guys with the 2 spark plugs, the coil of wire, and the, you know, whatever it is, and music in the background with no explanation of anything, and it's made in Africa or something. They're getting 2.4 billion hits, and I'm getting 150. So I guess they have discovered free energy after all.